All right, let's get into this. We're about to unpack a really fascinating story about how a pretty obscure mathematical tool is helping your phone hear a single signal in a massive digital crowd. It's something our brains do without even thinking. Before our devices, well, the solution is nothing short of brilliant. You know the feeling, right? You're at a loud party, music's blasting, dozens of people are talking, but somehow you can log on to one person's voice and follow the conversation. Our brains are just incredible at that. Well, our modern world is dealing with the exact same problem, just with radio waves instead of sound waves. I mean, just think about it. Every single device we own, your phone, your laptop, your smartwatch, even your fridge, they're all constantly shouting and listening for signals. We've got billions of devices all talking at once, creating this unbelievable amount of digital noise. It is a global digital cocktail party. And yeah, it's a big reason why your Wi-Fi sometimes just grinds to a halt. So, here's the issue. The ways we've been managing this crowd are starting to break down. For years, the solution was pretty simple. We'd tell the signals to take turns speaking, that's called time division, or we'd tell them to go into different rooms to have their conversations, that's frequency division. But with the crazy explosion of devices and the huge demands of 5G, we are literally running out of time slots and running out of rooms. We desperately need a new way for signals to talk right on top of each other and still be understood. To figure this out, researchers had to go right back to the very basics. And the first big clue lies in what a radio signal actually is once it gets turned into digital data. Now, I know this looks like something straight out of a math textbook, but trust me, this is the secret key to everything. It turns out that any radio wave, once you sample it and turn it into a list of numbers, is a perfect geometric sequence. It follows this exact pattern, where A is basically its starting strength and R is tied to its frequency. And here's where the problem really takes shape. Your phone's receiver doesn't get to hear one of these nice, clean signals. Nope. It hears the sum of all the signals hitting it at the same time. So as you can see here, you take three perfectly simple, predictable sequences, you add them together, and you get this new observed sequence at the bottom that just looks like a chaotic jumble of numbers. And that right there is the multi-billion-dollar question. I mean, look at that jumbled sequence. 7, 3, 21, 39. How on earth could you work backwards from that to figure out it was originally made from those three simple parts? To do that, you're going to need a really special kind of mathematical decoder. And here it is. To crack this code, researchers reached for a classic, heavy-duty tool from the world of digital signal processing. It's been around for a long time, but it's about to get a brand new and incredibly important mission. So if you've ever dealt with analog electronics, you might have run into something called the Laplace transform. Well, you can think of the Z-transform as its digital cousin. Laplace is built for smooth, continuous analog waves, but the Z-transform is designed specifically for discrete digital samples, which is exactly the kind of data we're dealing with here. Now, please do not get bogged down by the formula on the screen. The only thing you need to know is what it does. And what it does is pretty amazing. It takes that long, messy list of numbers from our jumbled signal, and it converts it into a single, clean algebraic function. It basically bundles all of that messy information into one tidy package we can actually work with. So why bother doing this? Because trying to analyze that endless, chaotic sequence of numbers is a nightmare. But analyzing a single, elegant function, that's something we can do. This tool gives us a powerful way to understand the hidden properties of that digital signal, and it sets the stage for the really clever part of this whole solution. Okay, prepare for the breakthrough. This is the part where researchers took that classic tool and combined it with a truly brilliant idea from geometry. This is a total shift in how to even look at the problem. So, let's go back to our starting point. We have our jumbled signal, which is really just a one-dimensional line of data points, all tangled up, seemingly random. This is our problem, laid out flat. The absolute genius of this new method is to just stop looking at the data as a flat line. Instead, the idea is to take these numbers and use them to build multidimensional shapes. It literally lifts the entire tangled mess up into a higher dimension where suddenly things start to make sense. And this is the core trick in a single image. By moving to a higher dimension, the signals that were all jumbled and overlapping suddenly reveal their individual identities. The hidden structure becomes perfectly clear just by changing your perspective. So how does this actually work? Well, it's this clever 5-step recipe. First, you take a guess at how many signals are mixed together. Let's say you guess there are 3. Then you use the data points from your jumbled signal to build a series of 3D shapes. In this case, they'd be tetrahedrons. Next, you calculate the volume of each of those shapes. And this right here is where the magic happens. This is the most amazing part. If, and only if, your guess for the number of signals was correct, the sequence of all those volumes you just calculated forms a brand new, perfectly simple, single geometric sequence. The chaos is transformed back into beautiful order. If your guess had been wrong, say you built 2D triangles when there were actually 3 signals, the volumes would just look like random noise. It's a foolproof test that lets you find the exact number of hidden signals, and from there, untangle them completely. So look, this is way more than just a cool math trick. What is the actual real-world payoff for this incredible geometric discovery? This quote from the researchers really nails it. We are running out of space on the airwaves. That phrase, orthogonal division, is just the fancy technical term for the old methods, making signals take turns or talk in different rooms. This new geometric approach lets them all talk at once, in the same room, at the same time, without it turning into chaos. It solves one of the biggest bottlenecks in modern technology. So what does all this mean for us? It means much more efficient wireless communication. It means we can pack way more users and way more data into the exact same slice of the radio spectrum. This is a fundamental game changer, the kind of technology that will power the next generation of wireless, and it forms the basis for new systems where interference is no longer the enemy. And at the end of the day, that just means faster, more reliable connections for all of us. And that really leaves us with a fascinating final thought. This technique, taking a complex, tangled-up problem and finding a simple solution just by looking at it in a higher dimension, that is an incredibly powerful idea. It solved the wireless cocktail party problem, but it makes you wonder, doesn't it? What other huge problems are out there, just waiting for us to find the right shape to solve them?